Okay, so I have started recording the video. 22 Feb. Today is 22 Feb. Yes, and I started the recording video. No problem. Okay, let's wait for. Okay, today's nobody have joined. Okay, let's see. Let's wait for a few minutes. Till then, I hope somebody will join. Okay, I'm waiting for people to join, but no, since nobody is joining, I have to start the lecture. So let me connect. Yeah, I need to share my screen. So this is our today's lecture PPT. Today's live session 22 Feb, live session 5th. I hope I'm recording. Yes, recording is going on, so no problem. Okay, so nobody is joining today. Okay, anyway, no problem. We will start. Okay, if someone comes, then I will admit them. Anyway, so welcome you all. So today is our fifth live session when I will be solving assignment. Few questions have left from assignment 3 and then assignment 4 this year and previous year. So I am Bhupan Singh, doing PhD in IIT Kanpur, from IIT Kanpur in the Department of Chemistry under the supervision of Professor Pratik Sen, who is the instructor of this course. So let's move on to assignment. Okay. So fourth question is, so fluorescence intensity of A and R in a solvent S respectively. So this so intensity of A is 5 into 10 to the power 5. Intensity of R is 7 into 10 to the power 5. When their respective absorbances, OD of A, 0.1, OD of R, 0.15. In solvent S, they are in the solvent S. Okay, given that the fluorescence quantum yield R of R in a solvent S is 0.3. So quantum yield of R is given 0.3. When the fluorescence quantum yield of A in the solvent S. So basically they are asking, okay, these all are in the solvent S. Fluorescence quantum yield of A. So this is totally formula based question. Nothing else is there. Right. So this is the formula for that to calculate the quantum yield. This absorbance, fluorescence intensity, and quantum yield. All the parameters have been given, so you will easily find out this. Just the calculation. Okay. So we are running 9 minutes late. No problem. 9 means 3 minutes late. Okay. Anyway, so today who can see who this? That's me. I'm presenting. Who is that? Shivam. What about Shivam? Is it okay? Hello, Shivam. I think he's not here. Oh, he's here. He's here. Yeah, tell me. Is it okay? Okay, then. Yeah, it is simple actually, so no problem. So I'm moving to the next question. Orientational polarizability varies A. Non-linearly with the second power of the dielectric constant of the solvent. Non-linearly with the second power of the refractive index of the solvent. Linearly with the dielectric constant of the solvent. Linearly with the refractive index of the solvent. So there are two quantity only, dielectric constant and refractive index. So we know the formula. This is the orientational polarizability formula, or the expression for the polarizability, orientational polarizability. So in the expression of orientational polarizability, the exponent of n is 2 and e is 1. The epsilon is 1. So you can simply say non-linearly with the second power of refractive index, because n is refractive index of the solvent. So answer is B. So answer is B. This is the same question from the class. Basically, not the class. Sir has actually shown this expression. I guess he is not derived from where this formula is coming, but this expression he has directly taken. So based on this expression, you can simply say that the orientational polarizability varies non-linearly with the second power of the refractive index of the solvent. Okay. Fine, Simon. Okay, sir. So, okay, moving on to the next question. For a solvent with a dielectric constant, eta is given. Refractive index of 1.2 at a room temperature. The electronic polarizability is okay. Okay, this is of the. I think this is anyway. So this is the same formula, electronic polarizability, FEL. Not the same formula. Sorry, not the same formula. Not the same formula, but this expression also discussed by sir, directly taken from somewhere. How this is coming, he has not told, but this is the formula. So anyway, the refractive index is provided, and this time they are not asking about the orientational polarizability. This time they are asking about the question is asking about the electronic polarizability. So for the electronic polarizability, this is the expression. So if you calculate just FEL, n square minus 1 divided by 2 n square plus 1. If you calculate it out, 1.2 to the power divided by 2 into 1 plus 2 to the power 2 plus 1. Then it will come out to be 0.11. So option B is correct. The calculation you can do. This is simple. Nothing. Okay, so no problem. Is it fine? Okay, moving on to the next question. So next question is, for a system, the slope found from the Lippard Mataka plot. For a system, the slope found from the Lippard Mataka plot is this. And if the radius of the cavity of the solute solution is found to be A, this is 4 angstrom, and the ground state dipole moment is 2d, t bar divide. Then the excited state dipole moment for a molecule is mu e. This is just a formula based, I believe so. Mm, Next question is also similar. For a solute molecule, the slope of this versus this versus this is this. So M1, M2 are given. For the expression of the ground state dipole moment is this. M1 and M2 are given respectively, and radius of the cavity A is also given. H is constant, C is constant, M you know. Then you can calculate the ground state dipole moment. And the ground state dipole moment is, just put all the values here only, as is Max Planck's constant. Joules. And C is 3 into 10 to the power 8 meter per second. The rest you know for this M1 and M2. M1 you know, M2 you know. And simply you will calculate using ground state dipole moment. This is fine. Answer will come out to be 5.65. This is okay. Slope is given. Oh, not this one. So slope is this for Lipat Matava. 2 divided by ca square mu e minus mu g whole square. So slope is 2 by HCA cube mu e minus mu c whole square. Slope is given, h I have already told, c you know, I already told, a is given, 2 is 2, mu g also is given. So according to the Lippard method, slope is this. Expression of the slope is this. So you will easily calculate the mu e. Fine. I'm just here to tell you the concept, because if I keep on calculating the mu e and mu z, then it will take much time, and so I'm here to actually make you conceptually rich. That's it. Okay, I've already shown you this formula according to the Lippard method. This is the equation. This is a very important equation. According to this equation, you'll get this slope. So the expression of the slope is this, and accordingly you can figure it out. The value of mu e for this expression, for this question. This question I have already told anyway. Next question. For a molecule, the slope of the plot this versus this is 0. The relation that must be true about the ground and excited state dipole moment is, this should be 0, because the slope in this equation, I remember this, yeah, this is written here. See, the slope is this. So the expression of the slope is minus 2 in bracket mu e square minus mu g square divided by HCA cube. So if the slope is 0, then mu e and mu g has to be equal. That is the condition. So that is what the question is asking. So this should be the answer. If you don't remember this expression, I can show you also for plus, yes, for plus, no. Hmm. Hmm. Mu absorption plus mu emission versus your full expression. Hmm. So this is the expression. Oh, connection is lost. Yeah, so what I was saying, okay, I'm back. Everyone is here. Yes, the screen is recording. So I was saying, what was the question? For molecule, the slope is this is zero. The relationship must be about between ground state and excited development is. So this is the question. This is the equation for plus. So the slope is this. Slope is this minus 2 mu e square minus mu z square divided by hc aq. And in question given is slope is 0. So mu e has to be equal to mu z. So the answer for this question is D. Okay. Next question is the Lippard-Matava plot for the molecule plot of two molecules A and B are shown in a figure given below. The correct statement is out of these four statements is change in the refractive index of A is greater than B, then radius of the cavity is same for the. So basically, what you can figure out from these two A and B, the Lippard Matava flow two molecules this one figure the correct statement is this. So basically, you can figure it out. The slope of A is higher and slope of B is lower. So A is greater than B. That we can know. That we can know from this graph. And what is the slope? Slope is not written here. Yeah, this is the formula, no? 2 divided by HCAQ in bracket mu g minus mu z mu v minus mu g का whole square. This is slope is mu z 2 divided by HCAQ in bracket mu v minus mu z का whole square. Okay, so what is the now the correct statement is according to this slope expression we can figure out which statement is correct. So they are asking for the correct statement. The change in the refractive index for A is greater than B when radius of cavity is same. I don't think so. In the expression of the slope, there is any involvement of the refractive index. Next, the change in the dipole moment for B is greater than A, and radius of the cavity is same for both. See, B has larger radius of cavity because they are not comparing this in question B. It is not compare. Oh, slope is already written here. Oh, nice. Yeah. So explanation, slope is already given. Slope is greater for A. Of course, and hence A is greater for B, as this is same for both. because yeah, a change in the dipole moment of for B, option B, change in dipole moment for B is greater than A when radius of the cavity is same for both. So basically, it is not like that, because this is the change in the this portion. This portion is the change in the dipole moment for V is greater. So if this portion is greater, then the slope will be higher for B. And fixing the, because this H is constant, C is constant, and you are fixing the radius of cavity, then the slope of V will be higher. But from the figure you can simply figure it out that the slope of the V is small than the A. So this option is wrong. And the first one, changing the refractive index for A is greater than the B, radius of the cavity, and radius of the cavity is same. So this is also wrong because in the slope there is no involvement of the refractive index. So first one is also wrong. Okay. Next, B has a larger radius of the cavity than A. Okay. When their dipole moment difference are same. So not at option C is saying this portion is fixed. Mu E minus mu Z is fixed. So 2 is 2. This is number. HC is fixed. They are varying the A. So if V has a larger radius of cavity, which means the slope will be less of B molecule than the A. So that is the figure is saying also. That is the same information you are getting from the figure. So this option is right. And what is the option D? There is no change in the dipole moment for either A and B. No, this option is not appropriate. Anyway, yeah, explanation is also given. The slope is greater, hence A is greater for B, as mu E minus mu Z is same for both. So option C is correct. Okay, Shivam? Shivam is listening. Okay. Okay, so let's move to the next question. Hmm. So now we are coming to the assignment 4. Assignment 4 for these are question from the this year. And after this I will be solving the question from the next previous year also. So the first question is, the fluorescence lifetime is generally independent of fluorescence concentration. Okay, fluorescence lifetime tau is generally independent of the fluorescence concentration. So tau, this fluorescence lifetime, I would say that this is fluorescence lifetime. This only belongs, this only, uh, this is the intrinsically property of the molecule. Intrinsic property of the molecule. So it doesn't depend on the concentration. So that is what the question is saying. Fluorescence lifetime is generally independent of fluorophore concentration, because fluorescence emission does not depend on the excited stage population. fluorescence emission does not depend on the excited state population. Lifetime depends only on the radiative and non-radiative decay. Yes. So lifetime is Kr plus Knr. This option seems appropriate. Fluorescence emission does not depend on the excited state population. Concentration affect absorption but not emission. That is also not true, because according to your inner filter effect, if you keep on increasing the concentration, the intensity of the emission will increase. When after certain concentration, the intensity will keep on decreasing because of the front surface absorption and the inner filter effect. So that is also not correct. Lifetime is determined by the solvent polarity only. No. So as I have already said, it is intrinsic property of the molecule. So fluorescence lifetime depend on only on the radiative and non-radiative decay. So that is why it is independent of the concentration of the molecule. So what is the explanation? Formula is written. It depends only on the intrinsic decay rate constant. Yes, concentration affect intensity. Yeah, that is what, no, intensity and concentration, but not decay kinetics. Yes, of course, unless aggregation or quenching occurs. That is one thing also. Yeah. That I must tell you that uh, even though these are the ideal situation, that increasing the concentration of the molecule, the lifetime will not going to vary, because it is intrinsic property of the molecule, and it only depends on the radiative and non-radiative decay rates, the kinetics. But if the concentration is too high, the chances of aggregation of the molecule forming the dimer from the monomer, or the aggregation or oligomers, will be higher. So, or maybe the quenching because of the formation of the dimer or trimer or oligomers. So then the lifetime of the molecule, will going to change. That is one condition also. But anyway, for now, for this question, that much information is sufficient. So B is the correct answer. Yeah. Moving on to the next question. Pulse. Who is there? Someone wants to join. Yeah, you are too late, Patlekha. You are joining after 45 minutes. I have already solved around how many questions? Sorry, sir. Sorry doesn't work like that. I'm traveling. Okay, no problem. So we have solved for you, Patleka. We have solved few questions from from the previous assignment. Whatever question we have left, we have not solved in the previous class. Fourth, fifth, sixth, seventh, eighth, and ninth and 10th question. And now we are solving this year's uh, week 4 assignment, and first question I have already solved. So the question is saying the fluorescence lifetime is generally independent of the fluorescence concentration. So I was telling that the fluorescence lifetime is the intrinsic property of the molecule. So that is why it doesn't depend on the concentration. However, and it depends on the the kinetics of the radiative and non-radiative decay. However, it depends on the concentration. When like it doesn't depend on the concentration, it is the ideal situation. But if the concentration is too high, then the oligomer, the monomer might form dimer, trimer, and oligomer. So in that condition, the lifetime of the molecule can change. Also, if by forming the dimer, trimer, they might the fluorescence intensity might quench and the lifetime might vary. So in that condition, the lifetime can vary according like by increasing the concentration. But ideally, it doesn't. The lifetime is intrinsic property of the molecule. It doesn't depend on the concentration. So if you, but of course, as I already mentioned about the inner filter effect, if you keep on increasing the concentration of the molecule, the intensity will increase of the fluorescence. But after certain concentration of the molecule, the intensity of the fluorescence will going to decrease, as I was telling here at this point. This is the concentration because of the front surface absorption and because of the inner filter effect. So that is why the option of this question is B. Lifetime depend only on the radiated and non-radiative decay rates. Fine. Yeah. Okay, so I'm moving to the next question. The next question is saying, let me check. Yes, 44 minutes. Yeah, it is recording. No problem. Okay, so now this is for you to solve. The pulse pileup occurs when see, yes, the photon detection rate is too high related to the repetition rate. So option C is correct. In TCSPC, only one photon per excitation cycle should be detected. High detection probability biases decay towards shorter lifetime. So what does it mean? I can explain you little bit. Hmm. So what is pulse pilot? Pulse pilot is emission is a random event. However, after excitation, more photons are emitted at the early time than at the later time. So in TCSPC, only the first photon is counted. Now, if the count rate is very high, always the first detected photon will be the first emitted photon. What does it mean? That in the TCSPC instrument, not let's say let's see here, this is your sample chamber. At this position, if your sample is getting excited, it doesn't necessary that the first emitted photon from this sample will going to be detected by the PMT. It can go here, this side, or anywhere. So it is not true that your first detected photon is first emitted photon. So so that is why it is written here. If the count rate is too high, then what will happen? The first detected photon, the probability of the first detected photon will be the probability of first emitted photon to be detected will be higher at the shorter time. So the if the count rate will be high, which means the number of photons, the frequency of the number of photon is higher to be detected. So what will happen at the early time? At the early time, so this is the time. This is the time. This is the intensity. Intensity. Early time at here, detection will be much higher. So if the count rate will be higher, then your emission, the lifetime data will look like this red one, because at the early time your PMT is detecting all most of the photons. So at the later time, let's say here or here, there is no photon left to be detected. Or I would say before, maybe at this position photon are getting emitted and PMT might detect. But before that, the count rate is before these emitted photon can come to the detector. The probability of, or the first emitted photon whose probability is higher, they will reach the detector much faster. So detecting of these photons will be higher than these photons. So again, as you know that in the TCS/PC only one photon can be detected at one time, then the tech will stop, the time will be, then the histogram, then the tech will stop, and this cycle will run for a millions time. I would, just for the approximation I'm saying, let's say it is running for the thousand or million times, then you will get the histogram, and from the histogram the data looks like this, your TCS/PC data. So that is why the count rate should be low. So now if the count rate is very high, always the first detected photon will be the first emitted photon. So first emitted photon means the lifetime is very short. So this means you will get the lifetime like this, the red one, whose the lifetime will be less, and the observed decay will be distorted. So count rate. So the count rate. So the count rate should be less than 2%, 0.02 photon per pulse detected. So we have to limit our photon counting rate less than 2% of the repetition rate of the light source. So in the instrument I have done TCS/PC for my during my PhD. Like my PhD is still going on, so I know how to manage this count rate. You can adjust the lens position, or you can adjust the slit width, or you can adjust the concentration of the molecule of your system, or you can, what you can do, lens position, slit width, concentration. Yeah, using these three options, you can adjust the repetition rate. So this has to be low. Otherwise, you will not get the correct emitted rate, the correct lifetime. So this is the pulse pileup. Okay. So the pulse pileups occur. The photon detection rate is too high related to the repetition rate that you have already told me. So option C is correct. I hope there is no problem. So I'm moving forward. Okay, Patlekha and Shivam. Okay, fine. So the next question. A TCSPC setup uses a pulse laser with a repetition rate is 20 megahertz. What is the maximum fluorescence lifetime that can be measured reliably? So if the repetition rate is 20 megahertz, which means the time. So by this information, you can calculate the time between the two pulses. So is the repetition rate you got. Now you can calculate the time. This time, this time can be calculated by 1 upon R. So divide this 20 megahertz. This is 8. 15 nanoseconds. So the time between the two pulses are 50 nanoseconds. So as you know that one pulse is coming, you are exciting the molecule. So this then the lifetime of the molecule has to be finished within this time. This time. So you know how to set the time window for to calculate the lifetime. So if you remember exact value, time window is 4.6 into lifetime. So let's say if lifetime is 1 nanosecond, then you have to set the time window to collect the lifetime to 4.6 nanosecond. So that is why because you are exciting, oh, because you are exciting here, molecule will come here and then slowly keep on decreasing. So that is why this window is very important. So lifetime you know 4.6 into lifetime. No. You know the time window. You know the time window 50 nanosecond. So lifetime you can calculate. If you take this 4.5 as a 5, 4.6 as a 5, then that lifetime will turn out to be the 10 nanosecond. This 10 nanosecond. See. So this is the maximum fluorescence lifetime that can be measured reliably. If the lifetime of the molecule is 12 nanosecond, let's say, then you have to increase the time window. But if any molecule have lifetime 8 nanosecond, that can be detected, that can be measured by this setup in that time window. So the repetition rate of that can be 20 megahertz, but cannot be uh, lifetime of that of the other molecule cannot be 12 nanoseconds. Otherwise, what will happen? The it is decaying from here, but the lifetime is high. So the fluorescence will not all the molecule from the excited state will come back to the ground state. Before that, another pulse will going to come. So again it will keep on decaying. So your spectra will be distorted. So that is why the time window is very much important to detect the lifetime of the molecule. I hope it is clear. Shivam, Patlika. Okay, fine. Moving on to the next question. Okay. So the next question is the solvent relaxation time influences fluorescence. The solvent relaxation time influences fluorescence when? This yes, this you have to answer. Any one of you. If solvent relaxation is lower compared to fluorescence lifetime, then the stroke shift occurs with time. So what? That is the explanation is written here. The solvent relaxation time influences fluorescence intensity. The solvent relaxation time influences fluorescence when so basically if the solvent relaxation time is lower than the fluorescence lifetime, which means that this is your S1 S1 S0. Now the dipole moment is here mu, here is mu z of the molecule. But the solvent around this have not stabilized, so it will come back. It will stabilize, and then it will emit. Nonetheless, it will stabilize, but if this process is much slower than the lifetime of the molecule, then what will happen? It will the molecule will not reach to its stable state. Before that, it will going to emit. So let's say your uh, solvent let's say solvent relaxation time is much higher. Let's say it's a very viscous solution. So the emission might come from here. Let's say it was in glycerol. Now it is in water. So viscosity is less, and the solvent relaxation time is also less. So then now the molecule will reach, let's say till here. It will emit from here. So that is why the relaxation time is slower than the fluorescence lifetime. It will influence the fluorescence. So that is why you will produce the dynamic stroke shift. That is what it is. So option B is fine, Patlika. Okay, both of you have agreed with me. No problem. Moving on to the next question. Next question is the fluorophore has a lifetime of 3 nanoseconds. What minimum observation time is required to record the 99% decay? 99% decay means let's say it is started from here, because 99% means all the molecules come down to the ground state from S to S0, from S1 to S0, from here to here. 99%. This is your 99%, let's say. Okay, so fluorescence lifetime has this. What is the minimum observation time is required to record the decay? I believe they are asking for the window. In the next, yeah, in this question I have already told. So basically they are asking about this time. Before the second pulse can come, before the second pulse can come, all the molecules, 99% of the molecules should decay. Otherwise, your spectra will be distorted. So they are asking about this window. What will be the minimum time or time window to record this lifetime? So this formula you know already. T equal to 4.6 into tau. So just 4.6 into what is the 3 nanoseconds. So I believe what's the 3 something like this is coming. Yeah, this much nanosecond. So this time window has to be 13 point more than 13.8 nanosecond. This is your T. And how to calculate this? This is 1% remaining. See this 1% remaining means I0. This equation you know, decay formula. This decay you know. I equal to I0 e to the power minus t by tau. So I divided by I0 is already given that 90%, 99% has already decayed. Means only 1% left. So 1 divided by 100. This much is only what this is the ratio equal to e to the power minus 1 by t by tau. So it turns out to be 0.001 e to the power minus t by tau. Now take the ln e of 0.1. ln will turn out to be t by tau, and if you calculate this, ln 0. minus of this here plus this. So if you calculate this minus ln 0.0 with 0.01 will turns out to be 4.6. So t by tau, and you will get t equal to 4.6 into tau. So what will be the this will be your correct answer, option D. Any doubt, Patlika, Simon? Should I move forward? Okay. Question number 6. Laser repetition rate is given or R equal to 1 megahertz. To avoid the pulse the photon detector probability must be less than this. This is funny, you know. So basically, the 2% of the less than the 2%, less than the 2% of your repetition rate So let's try to find out the 2% of repetition rate. This. So repetition rate. Oh, this sign is wrong. This should be like this. So repetition rate should be less than this. So this is the photon per pulse. So what does it mean? 0.02 photon per pulse means, let's say you are giving one pulse. Out of that 100 molecules are going to the excited state and emitting. Out of those 100, you are detecting only 2 photons. No, I think I have said wrong. Because here coming the 0.02 photons per pulse. Okay, I cannot say like this because it depends on the your repetition rate also. So how much repetition rate is there, that is also important. Anyway, according to this question, your answer should be C. Is it okay? Patlika and Sim. Yes, 2% of the repetition rate. Yes. Yes, you are correct, Patlika. So can we move to the next question? Okay. The main function of a constant fraction diffraction CFD is in TCSPC is to this you need to tell because there is no calculation. mm, no calculation, no formula you have to remember. Just you need to know what does this CFD does in your TCSPC instrument. Yes, reduced time jitter due to the amplitude jitter. So in the lecture, I think sir has covered already, but I will show you a little bit. Yeah, because of this, see, this is what, because of the threshold, because of the thermal noise, we have to keep the threshold uh, below this, below this signal. We are we are thinking that we are considering that these signal are from the noise. Um, these are the thermal noise. So we are giving the threshold till here. Okay, till this signal. So above this signal, here we are calculating that these are from my sample. Below this, it is from the noise. It is only noise. So that is why, even though both, let's say you have the first pulse is there, second pulse is there, not pulse, sorry, amplitude of the signal. Amplitude of the signal is there. Even you are considering that they are coming at the same time. See, look at here, coming at the same time. But because of the thermal noise, uh, you have to give this barrier. So that is why, see, if you plot this to this here, there is a difference between time here. See, this gap, this gap, this gap, this gap is coming. So this gap has to be minimized. Even though pulse of different amplitude are coming at the same time, but due to this noise, we have to put the threshold, and there is a time jitter between both the pulse. So to minimize that, we use the CFD. And what does this CFD do? It will actually bifurcate or 2 by 3 portion upper, upside, and 1 by 3 here. So then, by combination of these two, you'll get something like this. Something like this. So the difference between these two will be minimized. So this is what your time this CFD do in the TCSPC instrument. So this has been put after the your this detector PMT. Where is the setup? I'm not able to see TCSPC setup here. See, because even the PMT is detecting the photon at the same time because of the thermal noise. We have to put the threshold, hence we are getting the time star. So to minimize that, we are using the CFD. Anyway, making timing independent of the pulse height and minimizing amplitude induced jitter. CFD triggers the time signal at the post fraction of pulse amplitude. B. Okay, fine. Shall we move forward? Okay, moving on. Moving on to next question. This question is saying a bi-exponential decay has component tau 1, tau 2, 2 nanosecond, 8 nanosecond, 30%, 70%. This is amplitude A1, A2. By exponential decay has a component. The average lifetime is So we have to calculate the tau average. So tau average is A1 T1 A2 T2 divided by A1 plus A2. So if we convert this percentage into the fraction, so it will turn out to be 0.3. This is 0.7. Then you can calculate 0.3 into 2, 0.8 into 0.7 into 7 into 8. 0.3 plus 0.7. So 0.6 plus 5.6 divided by 1, so it will be 6.2 nanosecond. Option B. This is simple. What do you think, Patlika and Shivam? Okay. What about Shivam? Okay, fine. So both of you are good. Let's move to the next question. A photon reaches a detector at 0.8 nanosecond. The detector tangent, the photon reaches at a detector at 0.8 nanosecond. The detector tangent time is 35 picosecond. At what time will the electric signal appear? So this should be electric signal means. I can show you. See here. At here. So choose another color. Green. So at here. See, let's see here. In PMT at this point. You're getting the signal at 0.8 nanosecond. But this PMT has transient time spread, TTS, and this time is given as something like 50 some, how much picosecond is given? 35 picosecond. This is written as 35 picosecond. What do you mean by this 35 picosecond? Which means that the photon is reaching here at this point. Let me take another color, yellow. At this point, it will convert this signal, this photon, into the electrical signal. After, like, just what do you think? Let's say signal it is getting at here, the photon is getting at around after the 0.8 nanosecond. What do you think? As soon as it will reach to the detector, it will going to convert it to the electrical signal without any delay? No, because the detector already have some time delay, that is called the transient time spread. So that is 35 seconds. So it will take 35 picoseconds, 35 picoseconds to convert this electrical signal. So the according to the question, your answer should be, if we convert this 0.8 nanosecond, and if we convert this into nanosecond, it will be 0.035 nanosecond. So 0.035 nanosecond. It should be 0.835 nanosecond. Or if you convert this in picosecond, it should be 835 picosecond. if even it is reaching, this photon is reaching at after 800 picosecond, the signal will generate after 835 picosecond because of the PMT transient time spread is 35 picosecond. Okay, what do you mean by this transient time spread? Where is the detector? Yes, this is the detector. Or what happens is that, let's say photon is coming from this, follow my uh, this pen signal, the green color photon I'm drawing, this one. Okay, so let's say it is coming here, then it will take some time from here going here, then here, then here, then here. Of course it is multiplying, as you are able to see. Okay, then you are getting some time, then it is generating the here, then it is generating the signal, this your signal, your electrical signal, right? But let's say this is the total, this is the place open. Let's say photon is coming from here, next photon is coming from here, this side, this side. Now the again it will travel like this, and then, so the distance, the time between this photon and this will be difficult, will be different to be detect to be to generate the electrical signal. So let's say here at this point the t is, like the time is t0, time is t0. Here your the your PMT is getting the photon at t0 time, after t0 time. But one photon reaching here generating signal after, let's say, t1 time, another this one is generating signal after t2 time. So, and there are many photons, so there is a time range, and there of course the time range is very small, but there is a spread of the time. So that is why we have to add the time, total time to generate the electrical signal. It should be t tau t0 this time plus tt, because of this transient time spread. This is spread, no? For third photon, it will be 3, 4, tau 3, tau 4, tau 5. So there should be a one time window. So that is why it should be TTS. But if we try to make this transient time to 0, it is impossible to. There is no detector in this world have no transient time spread. All of the detectors have transient time spread. Anyway, the efficiency, of course, for ideal detector it is the requirement, and what are the other thing is required for this ideal detector? The constant gain. What do you mean by the constant gain? As I mentioned that for the green, the number of photon it is generated here, the here, and which is converted to the electrical signal at this point, it should be similar to your red one, but it is not the case. So the gain, even the photon of the same wavelength are coming, even the wavelength of the same wavelength of photons of the same wavelength are coming. Let's say lambda 4, let's say wavelength of the 450 nanometer of the wavelength. two photons of the same wavelength are coming. One photon, photon number 1, photon number 2. Even the electrical signal for this digit, or I would say, let's say it is generating a photon, let's say 1 lakh. For one case, another case it will be 95. And for another case it will be, let's say 1 lakh 10,000. Something like this. So there is not the perfect gain, like the constant gain. Gain is different. So of course this cannot be possible. So there is no ideal detector in this world. So anyway, coming back to our question. Yes. So this should be our answer. At what time will the electrical signal appear? So after this time the electric signal will appear. Okay, Patlika Shivam. What about Shivam? Okay, then move forward. Okay, a TCS/PC system has IRF of 120 picosecond. IRF is given. IRF is 120 picosecond. Minimum resolvable lifetime is approximately. So IRF means the instrument response function. So the IRF, how you calculate? You excite the molecule, you excite the, not excite actually, basically you, it is the count, it is the lifetime of the zero lifetime sample. So then you will get the, so according to, so let's say there is a sample or a scattered, I would say, you are not able to excite it. No, I mean to say, let's say there is a scatterer, you are exciting that. So it will not going to excite. What will happen? It will going to scatter your uh, light. Still in TCS/PC, you are getting some, you are getting the intensity and you are getting the lifetime. So this cannot be possible because your sample is zero lifetime sample. So which means this IRF is coming because of your instrument has some error. So this is the instrument error, instrument response function. So this you have to calculate before taking the lifetime of the molecule because it is the instrument error. So this you have to take first before taking the lifetime of the sample, and then you take the lifetime of the sample, then you have to deconvolute it. Anyway, so let's say your IRF is looking like something like this, right? If you take the data, your IRF somehow looks like this. Anyway, so how you calculate? You fit the IRF by Gaussian and take the full width half maximum. So basically, this is kind of the full window. Okay, this is kind of the full window. Full width half maximum is 120 picosecond. So what will be the resolution? It should be the resolution should be like 3 to 5 times divided by the 5 times. That should be the resolution. So let's say if it is 5 times, what is the IRF? 120 picosecond divided by 5, it turns out to be 24 picosecond. So which means 24 picosecond. Similar to this question. Oh, answer here written is B. So this is wrong, 100%. This is wrong. This should be A. This should be A. Because 60 is just half of the IRF. So this is not the resolution. So minimum resolution is divided by 5 times. Just like you are taking the window. Just let's say your molecule have lifetime of 3 nanosecond, right? Your lifetime of the molecule is 3 nanosecond. So how much window you will give to collect the lifetime of the molecule? Is 5 into 3. So the window at least has to be 50 nanosecond to collect the lifetime of the molecule. Molecule having lifetime of 3 nanosecond. Similarly, here you are getting the IRF by similarly you are here getting the lifetime by fitting this uh, spectra generating from the your uh, scatterer. So by fitting the Gaussian, you get the full width half maximum by fitting this by Gaussian. So basically, it is like your time window. So that is why time window just like this, and you are getting this from the full width half maximum. If this is your time window, this is your time window. You can figure it out. T divided by 4.5 or 5, then you calculate the lifetime. So lifetime means the minimum resolution of this IRF of the TCS system having IRF of 120 picosecond. So basically, if you in our case it is 24 picosecond. So let's say if your TCS system having IRF of this, and you are trying to calculate the lifetime of the molecule whose lifetime is less than 24 picosecond, which means let's say I am saying 15 picosecond. Tell me, will you able to will you able to calculate the lifetime of 15 picosecond using this TCS instrument? Patlekha and Shivam, this is for you. No, yes, because the resolution is 24 picosecond. So before that you cannot measure. It's just like you are having the meter scale and you are measuring the millimeter. You cannot measure the millimeter using the meter scale. Yes, you are correct, Patrika. Okay, what about Shivam? All good? Yeah, all good. What about Patlika? All good. Okay, so we are moving forward. Okay, now we are coming to the question of week 4 of previous year questions of previous year. Okay, first question is the femtosecond pulse laser working with repetition rate of 33 kilohertz repetition rate. The time difference between the two successive laser pulse. this time. Oh, this is simple. This is just 1 by tau. T equal to your 1 by repetition rate. See, it is simple. You can calculate it out. This is given 33 kilohertz. Flow is 33,000. Divide this, you will get 30 microseconds. So answer would be B. This I have already discussed many times. Right? Okay, fine. Moving on to the next question. For a measurement, for the measurement of the lifetime fluorescence lifetime of 4.5 nanoseconds. So lifetime is given of the molecule is 4.9 nanoseconds. The tag range which is not sufficient among the following is. So tag range means the time window. Time window, this also is simple. 4.6 into tau. So let's say I'm approximating this to 5. So it will be 5 into 4.5 nanosecond. Now you can calculate. In this also you can approximate by 5. So it will be like 5 into 5 is equal to 2.25 nanosecond. So this tag range should be must be longer than the your must be longer than the 25 nanosecond. See, it is written on a range of at least 5 times the lifetime is recommended. Since the fluorescence lifetime is 4.5, 15 nanosecond tag is too short and may not fully capture the decay. So answer is A, not sufficient. So 15 nanosecond time window is not sufficient. What will happen with, uh, in this case? In this case, the let's say pulse is coming, and another pulse after 15 second, 15 nanoseconds. Sorry for saying second. Anyway, here it is exciting. Let's say it is decaying. But before fully decaying till like 99% of your excited molecule come down to the excited to the ground state. Before that, your again another pulse is coming and exciting your sample. So again, it is going to dissociate like decay. So your lifetime observation will be the lifetime data will be distorted. So that is why it has to be more than 25 picosecond nanosecond. Fine, both of you Patlika Sivam. Okay. Okay, fine. Moving on to the next question. Okay, how much time I have left? How much time I have? 1 hour 42 seconds, 43 seconds. So I have still 17 minutes. So in 17 minutes, I have to finish this 7-8 questions. Anyway, next question is constant fraction discriminator CFD, which I have already discussed. CFD is an essential part of the TCS/PC setup. Its role is Patlekha Shivam, you need to tell me. D, same question. Yes, it is the same question. Yes, D. So I don't have to explain it again. Moving on to the next question. If the fluorescence lifetime decay of a system has two distinct components, 1 nanosecond, 5 nanosecond, 20%, 80%, the amplitude average lifetime. This is the same question, kind of same question. And explanation is also given here. Is it okay to you, Patlekha, Shivam, both of you? Same, I guess. I've solved this question in this class only. Okay, moving on to the next question. So the next question is for measurement of the lifetime of a molecule. If we intensely double the tag range, keeping the number of channels same. Basically, tag range means the time window. Let's say initially the time window was 15 nanosecond. Now double the tag range. Now it is 30 nanosecond. But the channel is fixed. But the channel is fixed. The recording time for the maximum count of 10,000 will be. Let's say you are fixing the maximum count is 10,000. So your TCCC data looks like this, and this is your 10,000. This is intensity number, photon count per second, 10,000. This is the maximum height is 10,000. So will be, so they are asking for the measurement of the lifetime of a molecule. Okay, how much time it will take to reach the 10,000 count, or intensity of this your molecule or this of your data will be 10,000. Right? So basically, as I have described here, see, in TCSPC system, the channel and bin essentially describe how the time axis is digitized. Channel means a channel is one discrete time slot in the multi-analyzer MCA histogram. Each detected photon is assigned to one channel based on its arrival time relative to the excitation pulse, which means is that the, let's say where you are making the histogram, no, so this time here is the channel window was there. Channel is one discrete time slot. This time slot is this. Let's say there are small fractions are the time slots. So in multi-channel, so we call this channel. So these are the these are the number of channels having the discrete time slot. Okay, so channel is the one discrete time slot in a multi-channel analyzer histogram, and each detected photon is assigned to one channel based on its arrival time. So basically, let's say your photon having the low lifetime is less, so it will be somehow somewhere detected here, will be detected here. So these these channel will detect this photon, or here these channel will detect. So basically one channel is based on its arrival time. So let's say your fluorophore intensity is like fluorophore is emitting at this point, so this channel will detect. Okay, so that is why each detected photon is assigned to one channel based on its arrival time related to the excitation pulse. Next, the total number of channel equal to total number of channels equal to total time window divided into discrete discrete intervals. So basically see this is the example is 4096 channels is common. So as I've already told that I'm using this TCSPC instrument on daily basis for my PhD. So in this setup I am fixing or using this 4096 channels. Like this is I'm keeping this fixed, and also you cannot go beyond this. Like if you want to increase this, I guess you cannot increase this from this more than this. So anyway, if let's say channel is 4096, which means that let's say initially, as I've already mentioned, the time window was 15 nanosecond. So the time interval, let's say this is 15 nanosecond from here to here, from here to here, this point to this point, it is 15 nanosecond. So the total number of channels equals to total time window is 15 nanosecond, 15 nanosecond divided into discrete intervals. So how many intervals? Let's say x interval. So basically each interval will be having the same time slot equal to 4096, this much channel. Now now they are giving one condition, that the measuring time, the tech range they have increased to double, it is 30. So condition is 30, the time window is 30, and your number of channel here written is the same number of channel, same, keeping the number of channel same. So it is 4096 again. So this what is this? Your time slot. This is no time slot. This time slot will be 2x, right? So which means that this same time frame. Oh no, this is not the same time frame. Now we have increased the time window. Okay, so it will be double of this, double of this. Let's say this, and so now time frame is this 30 nanosecond. But you are fixing the channel, which means time slot for every channel, time slot for every channel will be double compared to this case. That is why it is 2x. So if it is 2x, which means that let's say you are measuring or and that time slot is called the bin. So time slot or time bin width, or just simply bin, time bin width, or simply bin. So a bin is a time width corresponding to one channel, this x or 2x. So can be calculated by the total time window, which is 15 or 30, divided by number of channels. So 4963. And this is second case. First case is first 15 divided by 4096. Obviously, the width, because this is same, channel is same, this is same, so which means the total time window have increased in this case, which means the bin width will be higher in this case. So for example, 15, so here it is written that, for example, time window is 50 nanosecond, channels are this, so the bin width will be 12 picosecond. So considering that example, let's say I am increasing the time window to 100, 200, 200. What will happen? See, 100 nanosecond divided by the same number of channels. So simply it will be double of this, 14.4 picosecond. So each channel, per channel, the time bit or bin is 40, not 14, sorry. 24.4 picosecond. Double of this, double of this, double of this. Okay. Which means you are detecting the photon for 2x time. The time is increased. The time window is 2x compared to previous one. So basically, more molecule will be absorbed in that time frame, because time frame was this much initially. Now it is double. So in that time frame, more molecule will come. So which means reaching 10,000 count, reaching 10,000 count will be halved, because your time range has increased to double. So molecules will come at that time window will be twice of the previous one. Okay, so which means that your time measurement for the measurement of the lifetime of the molecule, a double will be halved. For the measurement of the lifetime of molecule will be halved if we intentionally double the take range, keeping the number of channels same. The recording time, no, recording time for the maximum of the count will be halved, not the lifetime, sorry. So the recording time for the maximum count of the 1000 will be halved. Okay. Yes, sir. Okay. Finally, what about Shivam? Okay. Okay. Moving on to the next question. I hope I may make myself clear. If a photon enters in a detector at 1 nanosecond and the transient time of the photon is 20 picosecond, the time at which the electrical signal will come out of the detector, this is the same question I have explained. Just convert this 1 nanosecond to picosecond or picosecond to nanosecond. So let's say I'm converting this picosecond to nanosecond and then add 1 nanosecond. So 1.02 nanosecond. That's it. Same question. Right, Patlekha and Shivam? Okay, fine. Okay, moving on to the next question. A sample has a lifetime of 20 picosecond less than 20 picosecond. Among the following instruments, the best technique to determine the time of the what I still have, because I have started after, so it's 1:59 46 seconds. So still I have 15 seconds. So anyway, a sample has a lifetime of 30 picosecond. Among the following instrument, the best technique to determine the lifetime is. Okay. Anyway, this question I will discuss in the next class. So from this assignment, from the previous assignment, how many question I have left? I was not able to solve 7, 8, 9, 10. 4 question. Anyway, in the next class I will solve. So as one of my students are saying, the time is up. I should stop because they are also getting bored. So it's 2 hours 50 minutes. Okay. Uh, both of you join in the next class, which will be going to happen on Sunday, same time, on 1st March. Yes, on 1st March. So yeah, and in the next class I'll solve the remaining 4 or 5 questions from this assignment, and assignment 5 and previous year assignment 5 will be solved in the next class. Till then, take care and have fun. Happy learning. Bye. I'm closing the session now.